Welcome back! Episode 9, Part 3 of this series, The Threat Landscape. We have spent the first 2 parts building the foundation vehicle architecture, cryptography, standards. Now we get concrete. We look at how attackers actually break into vehicles. This episode covers external interface threats, cellular, Bluetooth, Wi-Fi, USB, the OBD port, the UDS diagnostic protocol on top of it. The core message: every interface connecting your vehicle to the outside world is a potential entry point. An attacker only needs one unpatched Bluetooth stack, one dongle left plugged in, one open diagnostic session. That is all it takes. Let's go. This slide maps every external interface in a modern connected vehicle. Cellular and OBD2 rated critical. Bluetooth, Wi-Fi, UDS high. USB and V2X med. Notice the physical range spread. Cellular is worldwide. Wi-Fi is 100 meters. Bluetooth is 10 meters. OBD requires someone inside the vehicle. Each interface has a completely different threat model, but the key insight at the bottom applies to all of them equally. An attacker only needs one entry point. 10 perfectly secured interfaces and one misconfigured one. That one is all they need. Keep that in mind throughout this episode. The TCU cellular modem connects the vehicle to the OEM backend for OTA updates, telemetry, and emergency calls. That also means the vehicle is reachable from anywhere in the world, 24 hours a day. The attack window is unlimited. This is why the TCU is target number 1. Attackers use cell site simulators, CSS devices, and there are 3 main techniques. First, IMSI capture for location tracking. The CSS boosts its signal, the modem connects to it instead of a real tower, and the attacker reads the IMSI from the SIM card. The vehicle's location is tracked continuously without any driver indication. Second, communication interception. With the modem connected to the CSS, the attacker intercepts OTA payloads, telemetry data, and emergency call audio. Third, service downgrade. The CSS forces the modem from 5G down to 3G or 2G. The A51 cipher on 2G has been broken for over a decade. On a downgraded connection, the attacker reads everything in the clear. And at the extreme end, a compromised TCU blocking emergency calls is not a data breach. That is a life-threatening scenario. 4 Bluetooth attacks. 2 require absolutely zero pairing. Blueborn CVE 2017-10251, buffer overflow in the Bluetooth stack. Achieves OS-level code injection with no user interaction and no pairing required. An attacker within 10 meters silently compromises the IVE, then pivots to the internal vehicle network. KNOB CVE 2019-9506. Key negotiation of Bluetooth. Downgrades the session encryption key entropy to as low as 1 byte, 256 possible keys, brute-forced in milliseconds. Works against any classic Bluetooth device regardless of pairing. All Bluetooth traffic is then decryptable. BlueFrag CVE 2020-0022 exploits packet fragmentation to crash the target or inject arbitrary code. No pairing, no interaction. BlueSnarfing and BT Pineapple trick the IV into connecting to an attacker device and then exfiltrate paired phone contacts and location history stored on the IVI. Critical practical point from the handbook: Bluetooth OBD dongles left plugged in while driving create a direct Bluetooth to CAN bridge. An attacker within Bluetooth range connects to the dongle and gets on the CAN bus. Remove OBD dongles when the vehicle is moving. Wi-Fi threats. Evil twin attacker clones the vehicle's Wi-Fi SSID, IVI auto-connects, man-in-the-middle on all traffic, including OTA updates. Unpatched chipset firmware CVE 2019-15126 Cardoya allows Wi-Fi frame decryption without knowing the password. Chipset bugs sit below the OS and get missed in automotive patch cycles. Development ports left open in production SSH and Telnet with default credentials. Shell access. No further work required. USB threats. Malicious firmware via USB, a crafted file, exploits a parser vulnerability in the firmware update handler. Authentication bypass means arbitrary firmware installation. DMA attack via USB 3.x, a misconfigured or missing IOMMU lets a malicious device write payload directly into privileged system memory, bypassing every OS-level control. Bad USB device presents as a keyboard, injects keystrokes autonomously. Fully automated, zero user interaction. The OBD2 port, legally mandated. Under the dashboard. In many vehicles, a direct physical connection to the internal CAN bus with no network authentication protecting what is behind it. OBD connector pins 6 and 14 are CAN H and CAN L of the powertrain or chassis segment. Braking commands, steering commands, ECU resets all directly reachable. The most common real-world scenario, the aftermarket Bluetooth OBD dongle. 5 steps. 1 driver installs a cheap Bluetooth dongle and leaves it plugged in while driving. 2 dongle broadcasts Bluetooth continuously. 3 attacker exploits a Bluetooth vulnerability in the dongle firmware. 4 attacker now has wireless CAN bus access through the dongle. 5 arbitrary CAN frames injected spoofed speed, brake override, steering commands. Mitigations remove OBD dongles when driving. Implement CGW filtering, so the OBD port only reaches diagnostic service addresses. Require UDS authentication before any privileged session opens. UDS Unified Diagnostic Services. The language diagnostic tools used to communicate with ECUs. Every service is both a legitimate engineering capability and an attack vector. 8 services on this slide. 5 I want you to remember. X27 Security Access Seed Key Challenge. Weak seeds and reverse-engineered algorithms make it brute forceable. Xerox 34 and Xerox 36 request download and transfer data firmware flash. Pass authentication on Xerox27, and you can write any firmware to any ECU. Xerox 35 request upload reads ECU memory back to the client. Left in production, an attacker downloads the full firmware image, key material, and calibration data. Xerox 31 routine control triggers test routines, including actuator tests. Without CGW plausibility checks, brake and steering actuation runs at highway speed. UX11 EQ set force reboots an ECU mid-drive. 1 command. ABS reset during active braking. Direct safety consequence. Service Xerox 27, the legacy security mechanism uses a symmetric seed key challenge. The ECU sends a seed, the client computes a key using a pre-shared algorithm, sends it back. If it matches, the diagnostic level unlocks. The problem that shared algorithm lives somewhere accessible. Attackers reverse engineer leaked firmware and extract it. Short seeds are brute forceable, and the mechanism only provides level-based locking, no fine-grained control over individual services per client. Service UX29 replaces this with a PKI model. The diagnostic client presents an X509 certificate from the OEM's certificate authority specifying exactly which services it may access. The ECU verifies the certificate signature against a provisioned root CA key, then challenges the client to sign with its private key to prove possession. Result: no shared symmetric key on the device. Role-based permissions at the service level. Time-bounded and fully revocable access. A compromised diagnostic tool is blocked fleet-wide the moment its certificate is revoked. UX29 is where the industry must be for all privileged diagnostic access. No exceptions. 5 steps. Physical OBD port to persistent ECU code execution. Step 1. Attacker plugs a CAN sniffer into the OBD port, captures 10 minutes of traffic, reverse engineers the DBC maps CAN IDs to vehicle signals. Step 2. Service 0x10 opens an extended diagnostic session. Service 0x27 issues a seed. Attacker computes the key using a reverse-engineered algorithm from leaked firmware. Level 03 granted. Step 3. Service Xerox35 request upload was not removed from the production build. Attacker downloads the full ECU firmware image. Offline analysis finds the backdoor insertion point. Step 4. Attacker compiles patched firmware with a backdoor. Service 0x34, then 0x36 writes it to the ECU. No digital signature verification exists. Installation succeeds. Step 5. Backdoored firmware opens a covert channel through telematics CAN messages. Reboot does nothing backdoors in Flash. Attacker has permanent ECU control. 4 root causes. Weak UX27 seed key. No firmware signature verification. Request upload active in production. Missing CGW plausibility checks. Every single one is a known, documented, fixable problem. 4 defenses. These are minimum requirements, not optional enhancements. Cellular split APN at the carrier to restrict which IPs reach the TCU. Mutual TLS 1.3 with certificate authentication on every back-end connection. Monitor for protocol downgrade attempts. Rotate SIM credentials on schedule. Bluetooth mandate core specification 5.3 or later in your supplier requirements. Sandbox the Bluetooth stack from safety-critical code. Random pins for device pairing. Run software composition analysis on open-source BT components continuously. OBD and UDS CGW must enforce plausibility checks, blocking actuation routines while the vehicle is in motion. Migrate all privileged diagnostic access to Service 0x29 with PKI authentication. Permanently remove Service 0x35 request upload from every production build. Firmware every image installed via UDS or OTA must pass ECDSA digital signature verification before execution. No fallback. No bypass. No valid signature means no boot. Full stop. That is Episode 9. In Episode 10, we go inside the vehicle CAN injection, some IP attacks, Ethernet TSN abuse. See you there.